Okay, good. Okay, let's start. First of all, I want to thank the organizers for giving me the opportunity to give this talk at this interesting conference. This talk is based on work with Javier Campo and Sebastián Bustingorri from the Institute of Nanoscience and Nanotechnology of Argentina. The, the plan of the talk is as follows. I will start with a motivation, with a brief motivation, then I will describe some facts about the one-dimensional chiral solitons that appears in monoaxial Hilly magnets. Then I will show some results about the response of chiral solitons to a polarized electric current. And then finally, I will show also some results concerning the spin wave scattering by a one-dimensional soliton and some lateral shift that appears in the scattered wave, which is analogous to the Gauss-Hansen effect. And I will end with a discussion. And so the new results that I'm going to present here are based on these two papers. One is not yet published. Then let me start the motivation, recalling that solitons are now very crucial ingredients in the new revolutionary spintronic. The main problem with solitons is how to control them, how to move, how to create, how to arrange, etc. No, example of solitons are domain walls or skirmions, and also the one-dimensional chiral solitons, which are the main the main subject of this talk. Also, magnonics. We know that magnonics is becoming the paradigm of a new revolutionary technology, basically because it may allow the transmission and manipulation of information with ultra low power consumption. This is because in magnonics we try to send and manipulate the information and to transfer the information not by an electric current, not by charge motion, which dissipate much heat in the form of Joule heat, but only as spin currents, which do not imply the motion of charge, and therefore there is no Joule heat. But also, magnonics faces several crucial problems, and three of those problems are, for instance, we need to find materials with good magnonic properties. We need also to develop means to create and detect efficiently the spin waves, and we also need means to control the spin waves. And finally, as motivation. So the chiral magnets are very promising in spintronic and magnonics. They could be the main arena where the spintronics and magnonics processes take place. The reason is that they present robust non-collinear magnetic states, which are of topological and solitonic nature, and these states appear spontaneously and have interesting spin wave properties which are linked to the chirality. So this motivates the study of the solitons in chiral magnets, and basically the solitons I'm going to concentrate on the chiral solitons, one-dimensional, which appear in the monoaxial chiral Hilly magnets. These magnets are described by some energy, which is the integral of one density, and the energy density, ignoring the dipolar interaction, consists of one which describes the exchange energy. Then there is in this chiral Hilly magnet there is a Jalosinsky-Morilla interaction, which is of monoaxial type. So this interaction propagates only along one axis, which I'm going to call this axis. which is in our coordinate system, it is the Z axis, and I'm going to call it the DMI axis or the chiral axis. And then there is an anisotropy and an applied field. So the energy determines some effective field, the dynamics of the magnetization, which is in general a independent field, is well known. It is described by the Landau-Lipschitz-Hilbert equation, which has the usual reactive term, some Gilbert dissipative term, and we are going to consider also some external torque, which is delivered, for instance, by a polarized current. And this model has a static solution, which are, for instance, the homogeneous force ferromagnetic state in which all the spins are aligned. Then there is one solution, which is a single chiral soliton, which is located on a force ferromagnetic background, and there are also static solutions, which are the chiral soliton lattice, in which there are many solitons forming a lattice, and there is a helical state, which is the limit at zero field of this chiral lattice. So the force ferromagnetic state is the equilibrium state, the minimum energy, the minimum of the energy for if the applied field is large enough, and the chiral soliton lattice, the equilibrium state below some critical field, which is called C here. And what I'm going to show is that the isolated soliton is metastable. Is metastable on a range of the applied field. So if the applied field is too large, then the chiral soliton becomes unstable. But if it is low enough, then the chiral soliton is a metastable state. So the chiral soliton is a block soliton, so the magnetization lies on a plane perpendicular to the Jaruzelski-Morilla axis, which is the propagation axis of the modulation, and the angle which describes the soliton obeys the Sine-Gordon equation, and there are two possible solitons, which are characterized by the helicity. The helicity can be clockwise or counterclockwise. And what is interesting here is that the DMI provides, so the soliton is metastable always if there is no DMI, but DMI provides stability to the soliton with the proper chirality. So if the magnetic field, if the applied field is low enough, then the energy of the soliton with the proper helicity becomes lower than the energy of the ferromagnetic background, and then those solitons condense and form the chiral soliton lattice. Then the stability, we want to study whether the soliton is stable or unstable. To do this, we form some small variations along the soliton, and we may expand the energy in powers of this variation C. And the energy, the linear term is absent because this is a static solution of the Landau-Lipschitz equation, and then we have second order term, and the second order term is the energy of those variations at second order is described by linear operator K and Kz, and the condition of stability is that these two operators have to be positive, because the energy making a variation, the energy has to increase if the solitonic state is a local minima of the energy. Then it turns out that KT is a simple, relatively well-known Schrödinger operator. It is related to the post-Taylor potential, and then it be seen that Kt is always positive. So it is Kz which controls the stability of the soliton, and by studying the um, the spectrum of Kz, we can get the region of stability of the soliton. It turns out that the DMA and the anisotropy provide stability to the soliton. Without DMA and without anisotropy, that is in a pure Heisenberg ferromagnet, the soliton exists as a static solution, but it is unstable. However, the presence of DMI or isotropy gives stability to the soliton. Here we see the diagram. In this axis, there is it is plotted the anisotropy, and in the vertical axis it is the active field, and we see that soliton is stable in this blue region. The stability, of course, depends on the helicity of the soliton. So this line, this blue line, is the the stability boundary for the favored for the soliton favored by DMI. This line, however, is the stability boundary for the soliton unfavored by DMI. So in that case, DMI works against the stability of the soliton and tends to destabilize the soliton because the helicity is against the DMI energy. In any case, what we see here is that there is a large region of where the soliton can live metastate. And this is a good news for spintronics and also for magnetics. Then we can study how this static soliton behave under the application of a polarized current. The polarized current delivers a spin transfer torque which has this form. This is which is this is the reactive term, sometimes called the adiabatic torque, and there is also a dissipative torque, which is sometimes called the non-adiabatic torque, and which is the strength of the non-adiabatic is controlled by a parameter. Then, that if we apply the torque, the magnetization becomes time dependent. Then what we look, because we know that it is possible that the soliton is just dragged rigidly with some deformation, but rigidly, and it is moved under the action of the current. We look for a steady motion solution of the Landau-Gilbert equation with some constant velocity v. That means that the solution depends only on one variable W, which is set the spatial coordinate minus Vt. This is the time. Then the LLG equation becomes simply a boundary value problem for ordinary differential equations, which depends only on W. And the effect of the torque, the external torque, is encoded in these two parameters, omega and gamma. And these are the solitonic boundary conditions that have to obey the variables. It turns out, so we know that although initial value problems have always one and only one solution, boundary value problems may have no solution. That is, it may be impossible to satisfy simultaneously the equation and the boundary conditions. It turns out that this problem has a solution only omega, this value vanishes. And that means that the velocity has to be beta over alpha j. So the velocity has to be proportional to the intensity of the current. And so this means the velocity is uniquely determined by the current intensity as it should be. Also, we find that there is no solution if the current intensity is higher than some critical value Jc. So the steady motion takes place only if J, the current is smaller than the critical value. And the critical current. And the critical current depends on the characteristics of the magnet. For instance, the anisotropy, which is given by this parameter. It also depends on the applied field. So this critical current can be controlled by the applied field, and it decreases with the applied field. So what happens if the current is lower than the critical current is that there is a stationary solution in which the soliton move rigidly. It is deformed to a kind of conically deformed. So the width of the soliton change and depends on the current in the steady regime. And there is also a tilting characterized by this angle theta naught. It is tilted towards the chiral axis. Of the critical current, the boundary value problem does not describe the motion, of course, and we rely on NUMAX simulation, on numerical simulation to study this regime. And what we find is that the current destroys the soliton, and then the force ferromagnetic state is reached. We put here as a function of time, or these are the results of a numerical simulation. As a function of time, this cannot variable, which is a characteristic of the steady solution. So we see that if the current is lower than the critical current, this is the blue line. This soliton, which starts as the static soliton equals 0, is changed by the current, and then it reaches this variable reaches some constant. Some constant value which describes the steady motion. But if the current is higher than the critical current, then the variable is not stabilized as it grows, and then it goes to 0. And there is a start at which the soliton, at this point, the soliton is destroyed and the ferromagnetic state is reached. So we can plot this start time, which is the time at which the soliton is destroyed, versus the current, and we see that for large current this time is small, but it increases, and at the critical current is diverges. Below the critical current, this time does not exist because the soliton is not destroyed. It moves. It moves with constant velocity. So this is interesting because this current allows to either move the soliton or raise the soliton, which is an important thing in spintron. Then, after describing the response of a soliton to an applied current, let me describe what is the spin wave spectrum in the presence of a soliton, and the spin wave and the some features of the spin wave scattering by the soliton. So we start with some soliton described by naught, which is the variable describes the soliton, and then the variation Ct is describing the spin wave which propagates in presence of the soliton. The magnetization dynamics is described by the Landau-Lipschitz-Gilbert equation, and we are going to know the damping term. We can, if the distortion is small, we can linearize the Landau-Lipschitz equation, and then what we got is a linear equation for the variation C that describes the spin wave. So we can call that spin wave equation, and this omega operator is related to the K operator that appear in the energy of the variation. Then in the case of the soliton, the omega operator is the spin wave operator is relatively simple, and we can decouple the equation for the two components and study just one single equation, which resembles Schrodinger equation, but which with an operator which is fourth order in the derivative, so it is different from Schrodinger and it is non the function. This causes some technical problem. But no, in but anyway, we can see here that the two operators, omega 1 and omega 2, that describe the spin wave dynamics are like Schrodinger operators. There is there is a Laplacian term which appears, which gives the effect of the exchange of the exchange interaction in the spin waves that propagate on the ferromagnetic part of the system, and U1 and U2 are potentials that are like a potential in the Schrodinger equation, which are caused by the soliton and which are localized at the position of the soliton. So if we are far from the soliton, the potential vanish, and then we have the propagation of a spin wave in a ferromagnetic ground. Now this is the setting I'm going to use. So I use it to the two-dimensional setting. This set is the direction of the DMI axis, and the soliton occupies. And in the transverse direction X, there is no variation, so the system is homogeneous. The magnetization is the same. The static magnetization is the same along those lines. So we can consider a spin wave that basically in that region, which is essentially ferromagnetic, and then it goes towards the soliton. Now we can see what happens to the spin wave. Then the spin waves are waves in the x direction. We can found the spectrum by solving a one-dimensional problem, even if we are in 2 or 3 dimensions. And the spectrum contains one bound state, which is given here the red line. So this is the spectrum omega versus the x. X is the wave vector in the transverse in the x direction, and here it is plot the state. And we see that besides this bound state, there is a continuum of state with a gap. So the bound state describes waves which are bounded to the soliton, in the sense that the amplitude of this wave decreases exponentially with z of the soliton. They propagate along this direction, so they can be this wave can be used to transfer information from one side the other of the system, because so in that sense the soliton acts like cable, or better like a wave guide, or as in electrodynamic in electromagnetic waves. This acts as a guide for the spin waves.
5 minutes.
5 minutes. Okay. Then for the continuum. The continuum spectrum describes waves which are not bounded to the soliton. So those waves travel the soliton, they cross the soliton, they are transmitted and reflected, so they are scattered. What is the properties of this continuum state is first that the dispersion relation, so that is the relation of the frequency. The wave numbers is the same as the ferromagnetic state, because basically they are always in the ferromagnetic state, because the soliton occupies only a small portion of the system. The system is very large, and the soliton is concentrated on one region. So the effect of the soliton is to give some phases the amplitudes of the scattered waves, which are called the phase shift, and those phase shifts depends on the wave numbers. So this is basically here I summarize the effect of the soliton. The soliton does not change the continuum spectrum. So the spin wave have the same dispersion relation and the same gap. It modifies the eigenfunction of the amplitudes of the continuous state by introducing the phase shift, and also introduce a bound state. This is a purely an effect of the soliton. There is no soliton, there is no bound state. So here you can see the phase shift delta, which are the key ingredient, the key ingredients for studying the scattering as a function of kz. This is for kz equals 0, and you see that it depends on kz as usually. So Levinson theorem. This is curious because Levinson theorem, which is a theorem of quantum mechanics, which relates the behavior of the phase shift at 0 and at infinity with the number of bound states, is satisfied. It is satisfied even if we are dealing with an operator which is omega 2 times omega 1, which is not of Schrodinger type. But Levinson theorem is satisfied. The reflection coefficient does not vanish. I mentioned that because in the scattering by a domain wall, the reflection coefficient vanish, and the phase shift depends on k. And the dependence of the phase shift on the transverse wave vector, which does not, this dependence does not happen in quantum mechanics. This dependence means that a lateral shift of the scattered wave is introduced, and the lateral shift is given by the derivative of the phase shift with respect to the kx, with respect to the transverse wave vector. This shift is similar to the Gauss-Hansen effect that appears in optics, and we may picture this like a spin wave which approaches. There's an incident wave that approaches the soliton, and then the effect of the soliton is that some part of the energy is reflected and another is transmitted. But now, because of this shift, the reflected and the transmitted energy, so the reflected and the transmitted wave packet, are shifted from the direction of the incident propagation. So this effect can be used to control the spin waves. This shift can be seen, that appears like as a can be seen. The origin of the shift is can be seen from a stationary phase analysis. So if we form a wave packet, then we know that the center of the wave packet is where the constructive interference appears, and these are at the place where the phase is stationary with respect to kx and ky, and the fact that the scattered wave have a phase shift means that depends on kx, means that the center of the wave packet is this shift. This can be also seen as a kind in the geometric optics limit as the refraction of the spin wave when it enters media, and then the refraction causes this shift. But be careful because we are very far from the geometric optics limit, because the wavelength is of the order of the.
You need to finish.
Yes, I finished. The wavelength is of the same order of the width of the solid. Then just to finish, what I have to say is that what is what is the size of this shift? The problem is that the shift is a fraction of the wavelength. As you see here, there's a plot of the shift versus frequency for different incidence angles. There are several possibilities. When it is irrelevant, well, it may be irrelevant because it is a fraction of the wavelength, but I have to point out that the transmission coefficient is additive. Is almost one, and the shift is additive. So if we set an array of solitons, the shift will be enhanced by a large factor without losing the intensity of the spin wave, because the transmission coefficient is nearly one. So this is basically what I wanted to say. Many thanks for the attention.
Hi, thank you very much for the very nice presentation. I was wondering, so because you investigate the scattering of the spin wave on a one-dimensional soliton, does all this stuff also apply in case when you transition to the two dimensions, that you basically scatter the spin waves on a skyrmion or anti-skyrmion, or how does this frequency shift basically change in that case?
No, the results depends crucially on the one-dimensional nature of the solid. In two dimensions, the scattering is different. You have to use the partial wave expansion, etc. But this has been already studied by Marcus Garst and his collaborators. So there are works in the scattering of solitons by skyrmions in two dimensions. But here, the shift, for instance, this shift is a feature of the one-dimensional scattering. In two dimensions, what it appears is some deflection of the solid. It is
Thank you.
In two dimensions. It's like scattering by a central potential.
Okay. Thank you.